There are many techniques that can be used for dimensionality reduction. In this lesson, in this section, let's review a few main techniques. Perhaps the most common are the so-called feature selection techniques that use scoring or statistical methods to select which features to keep and which features to delete. Two main classes of feature selection techniques include wrapper methods and filter methods. Wrapper methods, as the name suggests, wraps a machine learning model, fitting and evaluating the model with different subsets of input features, and then selecting the subset of features with the best model performance. RFE is an example of a wrapper feature selection method. Filter methods use scoring methods, like correlation between the features in the target variable, to select a subset of input features that are the most predictive. Examples include Pearson's correlation and the chi-squared test. Techniques for linear algebra can be used for dimensionality reduction. Specifically, matrix factorization methods can be used to reduce a dataset into its constituent parts. Examples include the Eigen decomposition and the singular value decomposition methods. The parts can then be ranked, and a subset of those parts can be selected that best capture the salient structure of the matrix that can be used to best represent the dataset. The most common method of ranking these components is called principal component analysis, or PCA for short. Techniques for high dimensionality statistics can also be used for dimensionality reduction. These techniques are sometimes referred to as manifold learning and are used to create a low dimensionality projection of a high dimensionality data space, often for the purposes of data visualization. The projection is designed to both create a low dimensional representation of the dataset while best preserving the salient structure of the relationships in that data. Examples of manifolding learning techniques include the cone self-organizing map, Sampson's mapping, multidimensional scaling, and a t-distributed stochastic neighbor embedding. The features in the projection often have little relationship with the original columns, i.e., they don't have column names, which can be confusing to beginners. Next up are the autoencoder methods. Deep learning models can be constructed to perform dimensionality reduction. A popular approach is called autoencoders. This involves framing a supervised learning problem where a model must reproduce the input correctly. A neural network is then used that seeks out to compress the data flow of the bottleneck layer with far fewer dimensions than the original input data. The part of the model prior to and including the bottleneck is referred to the encoder, and the part of the model that reads the bottleneck output and then reconstructs the input is called the decoder. After the training, the decoder is discarded, and the output from the bottleneck is used directly as the reduced dimensionality of the input. Inputs transformed by this encoder can be fed into another model, not necessarily the same neural network model. The output of the encoder is a type of projection, and like projection methods, there is no direct relationship to the bottleneck output to the original input variables, making them challenging to interpret.